just general students or?
Sir, I mean, the talk is open for all, so mostly are physics people, but it is a mix. Like every interested person can come in.
Mm, okay.
Yes. Sir, can you wait for 3 more minutes or should we start now?
It's up to you. Yeah, I can wait.
Yes, sir. People are coming, so just kindly. Hello, sir. We are starting now.
Okay.
Good evening, everyone. Thank you very much, all, for joining us today for another interesting talk of our online seminar series. I am sure almost all of us must have heard the term quantum at some point of our life, and let it spark a curiosity in our minds. As what is quantum? How quantum theory works? What quantum particles are and how they are related, and many more. Though such questions occupy our brains at times, we often dismiss the significance of these concepts in our daily lives. Yet, across borders, laboratories tirelessly work on technologies that not only utilize but also push the boundaries of quantum understanding, aiming to unravel fundamental questions and drive technological advancements that impact our daily, everyday existence. In this online talk, we will journey through the wonders of quantum entanglement, a phenomena that defies classical logic and binds particles in a way that challenge our perceptions of reality. Join us as we uncover the profound implications of quantum principles and explore how they shape not only our understanding of the universe, but also the technologies that shape our world. From revolutionizing communication and computing to enhancing medical diagnostics and encryption methods. Discover how these quantum advancements are shaping the future, influencing everything from the devices we use to the way we perceive the world around us. Without further ado, I would like to introduce Professor Subir Sachdev, who is currently a Herschel Smith Professor of Physics at Harvard University. After completing a Bachelor of Science in Physics from Massachusetts Institute of Technology, Professor Sachdev did a Master of Arts in Physics, followed by a PhD in Theoretical Physics, both from Harvard University in the years 1982 and 1984, respectively, along with an MA honorary degree from Yale University in 1995. He held professional positions at Bell Labs from 1985 to 1987 and at Yale University from 1987 to 2005, where he was a professor of physics, before finally returning to Harvard, where he is now the Herschel Smith Professor of Physics since 2015. Additionally, Professor Sachdev was elected as a foreign member of the Royal Society in 2023, a member of the American Academy of Arts and Sciences in 2019, an honorary fellow of the Indian Academy of Sciences in 2019, a member of the US National Academy of Sciences, and a foreign fellow of the Indian National Science Academy. Professor Sachdev is a prominent theoretical physicist specializing in condensed matter physics with a significant focus on quantum entanglement and quantum phase transitions. His research has made substantial contribution to understanding complex quantum entanglement in materials such as high temperature superconductors and strange metals. One of his notable contributions is the development of the Sachdev-Ye-Kitaev SYK model, which has provided deep insights into the quantum properties of strange metals and their connections to black holes. This model has revealed a fascinating link between the thermalization processes in strange metals and the quantum chaos observed near black holes, helping bridge the gap between condensed matter physics and gravitational theories. In addition to his research, Professor Sachdev has authored several influential books, including Quantum Phase Transitions, Holographic Quantum Matter, and Quantum Phases of Matter, which further explore the nature of quantum materials and their critical behaviors. Also, he has received several prestigious awards recognizing his significant contribution to theoretical physics. Some of his notable accolades include the Dirac Medal in 2018, awarded by the International Center for Theoretical Physics. This medal is one of the highest honors in theoretical physics and recognizes Dr. Sachdev's pioneering work in quantum phase transition and quantum criticality. The Lars Onsager Prize 2018, presented by the American Physical Society. This prize honors outstanding research in theoretical statistical physics, an area where Dr. Sachdev has made significant contributions. Also, the New England Choice Award for Academics in 2018. This award recognizes excellence in academic achievement and contributions to education and research, and many more awards. I would now like to kindly ask and request Professor Subir Sachdev to begin his talk and enlighten us with his knowledge and experience on quantum entanglement. Sir, please.
Okay, excuse me. So thank you, Ayush Narayan, is that your name, I guess?
Yes, sir.
Thank you for that really kind and thorough introduction. Everything was completely accurate. I just want to mention one more thing. I actually started my education at IIT Delhi. Uh, so as an electrical engineer, those days there were no ICERs around. Uh, and before moving to MIT in the middle of my undergraduate education. And I've visited a few ICERs. I think I've been to Pune and Mohali and also in Kolkata. So it's a pleasure to meet you all. And please don't hesitate to interrupt during my presentation if you have a burning question or something is not clear. Okay, so let me begin my presentation then. Share the screen. Oops, what happened? Okay. All right, so I presume you can see my screen and also my pointer. Right. So the theme of my talk is quantum entanglement and its implications for modern physics. The idea of quantum entanglement, in some sense, starts in 1865, as I'll explain now, although you might be surprised to hear that early date, because quantum mechanics itself was not formulated until 1927. So what was this pioneer? Well, the pioneer was a chemist, German chemist named Kekule, who was thinking about the structure of benzene, the molecule with 6 carbon and 6 hydrogen atoms. So it was known to chemists that benzene had to have a ring of carbon atoms with, and then some of the atoms had to be, carbon bonds had to be double bonds and some single bonds. And so there was a dilemma on how to place the double bonds. So if you make an arrangement like shown here, where the ellipses represent double bonds, then the perfect hexagonal shape of carbon would be distorted. And then there's, of course, an alternative location, which would distort it the other way. And of course, Kekule came up with the idea of resonance, claiming that it was actually both. It was resonating between both. So today we have a much more sophisticated understanding of this phenomenon. And we can think of it as in the entanglement of 6 electrons. So each one of these ellipses represents what's called an EPR pair. And I'll say a little bit more about this shortly. See here, I'm just representing the spin of the electron, which can point either up or down. And in a valence bond, the electrons pairs are entangled. So you could have one electron with spin up and the other electron spin down. That's one possible state. And the other possible state has the opposite arrangement. And quantum mechanics, the most fundamental principle of quantum mechanics is the principle of superposition, which says that physically distinct states can be combined in a superposition of quantum state. So in this case, you could superpose the up-down and the down-up and get this valence bond. So that's the entanglement of 2 electrons in the valence bond. And what Kekule had unwittingly discovered was an even deeper level of entanglement, where you have entanglement between, all 6 electrons in this manner. All right, so that's really all entanglement at some basic level. It's everywhere. It's in every covalent bond in organic chemistry. And in benzene, it's a little bit more elaborate because the bonds themselves are entangled with each other. Okay, so that's the picture that was being developed by quantum mechanics in the 1920s and 1930s. But not everybody bought this picture. And in particular, Einstein, Podolsky, and Rosen wrote this famous paper in 1935, which can be viewed as really the start of quantum entanglement, although they didn't use that word in this paper. And they questioned the idea that this picture of entanglement, could it really be the final story? And the reason they questioned it, because it led to a phenomenon that's called spooky action at a distance. And I've always wondered if Einstein had actually said that. In fact, he had. This is spooky action at a distance, Spukhafte Verneverkungen, I guess, in German, in a letter that Albert Einstein wrote much later to Max Born in 1947. And he said that he just can't believe that such spooky actions at distance are present. So what was he referring to? Was he referring to this type of thought experiment, which today is no longer a thought experiment, has been done many times in the lab? So you imagine you take this entangled pair of two electrons that I've mentioned here. You could think of it as a covalent bond between two hydrogen atoms, where the spins of the electrons could either be in this state or this state. And imagine that you could separate the two electrons or even the two atoms without disturbing their spin. So one electron would be here, and the other electron would be there. And these could be, in principle, infinitely far apart. And quantum mechanics says that as long as the spin was not disturbed, they would still be entangled. So this leads to some rather remarkable consequences. Because if I have this electron in my hand and I measure it, then quantum mechanics says that at that point, once I measure it and observe it to be, say, down, then the whole quantum state has collapsed into the state that I measured. In particular, the state of the other electron, which could be really far away, has also collapsed. And since they're always anti-correlated, if this is down, the other one is up. Okay, so this seems like some very strange, spooky action at a distance, where measurements here are influencing the state of the electron over there. And this is really what Einstein, Podolsky, and Rosen found really objectionable, and they were sure, if you read their paper, that there was going to be a better answer eventually to this consequence, what seemed to be a logical consequence of the principles of quantum mechanics in 1935. In fact, today we know there is no other answer. This experiment has been done, and it indeed does work exactly the way the original principle of quantum mechanics predicted they would. And, I don't know if you have any better understanding of it, why the world is this way. But I think the basic idea that you have to absorb is that the quantum state of these two electrons is not a property of either one of them. So it's not as if something is traveling from one quantum state to the other quantum state of the two electrons. The quantum state doesn't exist either near or there. I mean, the electrons in the past were next to each other, and that's when they got entangled. And that state was not a property of either electron. Okay, so there's a certain non-locality, but there's no violation of causality or even the fact that no signal can travel faster than the speed of light, because the second observer over here has no knowledge of what's happening with the first observer over there. It's only when they communicate later that they can verify that things happen as quantum mechanics predict. All right, so that was a thought experiment in 1935, but quantum entanglement has moved from being, just a philosophical issue that some physicists worried about, but most experimentalists didn't care, to something that is really important, even in experimental science. And there's many different developments in modern physics which now depend on quantum entanglement. Most famously, of course, are quantum computers themselves, in which you try to control the entanglement of many, many qubits. That's an exceedingly hard task, and it's not clear where that is going to go to. Although it's very clear we're learning a lot more about quantum mechanics along the way. So I won't talk about that, but I'll talk about the next two topics, where it's turned out that for example, multi-particle long-range quantum entanglement is needed to understand, basic materials that we made in the lab, and they have some remarkable properties and they can really be understood if we think about entanglement in a much more general sense. Another place where entanglement has played a fundamental role is in the black hole quantum information problem of Hawking, and what is the structure of a black hole. And I'll say also a bit more about that shortly. All right, so let me begin with modern quantum materials, and the class of quantum materials I want to focus on are superconductors. So superconductors were discovered in 1911 by Camerlionis when he cooled mercury to 4 degrees Kelvin and discovered that it transferred current with zero resistance. So that was quite a remarkable property, but you had to cool things down to very low temperatures. This is the big refrigerator that you can go and see in Leiden even today. But here I want to talk about a new class of superconductors that were discovered in 1986, the so-called cuprate superconductors. One famous example of them is yttrium barium copper oxide. Here's a little piece of it. This is kind of what it looks like, but this is a chemical structure, extremely complicated. But fortunately, all of the important physics happens on this square of copper atoms, where in fact they form a square lattice. So you just have to worry about a single square lattice of copper atoms and a single orbital on each copper atom. So the underlying physics is still quite complicated because of the entanglement of the electrons between these copper atoms. And that's something I'll say a little bit about very shortly. Okay, so the superconductor is extremely useful. Well, since it can superconduct at temperature, sorry, I forgot to mention, I think I'm missing a slide here. Doesn't matter. The superconductor can transfer electricity with zero resistance at temperatures above the boiling point of liquid nitrogen, which is 77 degrees Kelvin. And it's quite easy to make liquid nitrogen. And so you can use this little ceramic piece of yttrium barium copper oxide. And today people have learned how to make big magnets out of them. And these magnets are extremely powerful because they can create strong magnetic fields in a very compact region. And that's one of the possible uses of this, which is this company called Commonwealth Fusion Systems. They're trying to take these magnets of yttrium barium copper oxide to produce fusion energy. Well, let's see if they succeed, but this is an example of how new materials change the very possibilities of things that can be achieved by modern devices. Okay. All right, so here's getting down to the physics of it. Here's a little more information about such a material. On the horizontal axis, I have the density of electrons on this copper plane. And that's changed by just changing the value of X, the amount of oxygen away from the planes. And vertical axis, you have temperature. And my focus here is really on this yellow region, where at certain densities of electrons, the system is a superconductor at temperatures as high as 100 degrees Kelvin. So this is much, much higher than the 4 degrees Kelvin or even that Camerlionis found for mercury. All right. So one of of course, the big open problem in the field is to figure out what is this critical temperature. And that's not something that we are able to do today. And partly because the state above TC turns out to be rather complicated. So if you look in this blue region and measure the properties of this material, it behaves very similarly to an ordinary metal like copper or gold or something like that, other than the fact that it has a superconducting transition temperature that is relatively high. So we can do a theory of this ordinary metal and try to figure out why it goes superconducting, and we have some understanding of that today. But this is not the interesting region. The interesting region is right up here where the TC is the highest possible. And there you have a rather bizarre metal, which for want of a better name is now called the strange metal. And what's so strange about it? Well, I won't go into all of the details, but I'll mention a few of the strange properties. One of which is that if you measure the resistivity above TC here as a function of temperature, so here's a plot of the resistivity as a function of temperature. Note the resistance goes to 0 in this particular material at around 40 Kelvin or so. But above TC, then you have this very wide window where the resistance is a linear function of temperature. And it's this famous linearity resistivity that's one of the strange properties, because if you were to take either YBCO at this in the blue region or copper or gold, you wouldn't see this. You would see a quadratic dependence on temperature. Now, okay, so that might seem, like a minor difference, but there's something very fundamental about the quadratic dependence. And to explain that, I need to go back and review some physics of what happens of electrons in ordinary metals. And to do that, I'm going to go way back to Boltzmann, who really laid the foundations of statistical mechanics, where we understand the behavior of trillions and trillions of particles, say electrons in a given metal. Of course, Boltzmann didn't even know about electrons. He was thinking about the molecules of the gas in this room, and trying to understand the property of ideal or nearly ideal gases. And through that, he made two very fundamental contributions. One, that he came up with the fundamental definition of entropy. The entropy S is Boltzmann constant times the log of W. So as you can see, he was clearly very proud of it. It's on his gravestone in Vienna. And what does this mean? So entropy was a concept that had existed for a while in physics before Boltzmann. It was a concept in thermodynamics, where one of the principles of thermodynamics was that you can't have perpetual motion machines. And this was formulated by the statement that the entropy of any system has to always increase. What Boltzmann proposed was the entropy was a fundamental quantity that could be defined in any equilibrium state of the gas, just like its pressure or temperature or volume. You would also measure you could also define the entropy. And the fundamental definition of entropy was it was a logarithm of W. And what is W? W is, roughly speaking, a measure of the randomness of the gas, or the number of possible microscopic states of the system that are compatible with the macroscopic properties that are observed. So this is an exponentially large number, where in the number of atoms, so it's e to the Avogadro's number. W is a huge number, but when you take its logarithm, it becomes proportional to Avogadro's number. And so it becomes what we call an extensive quantity, like the entropy itself or the volume. These are extensive quantities. Okay. So one of the remarkable things is that although this was for classical mechanics, entropy, the Boltzmann definition survives the introduction of quantum mechanics. You just have to replace W by the density of quantum states. So quantum mechanics tells us that the energy of any quantum system, some finite quantum system, is always discrete. So you take some small energy interval and you ask how many quantum states do you have. For a many-body system, that's also an exponentially large number. And the logarithm of that, of d of e, is then s of e. Also, this I should have mentioned a bit earlier, Boltzmann definition of entropy also gave a fundamental definition by this equation of the absolute scale of temperature that we use today. Okay, so that was 1870. Shortly after, in 1872, Boltzmann came up with what we call the Boltzmann equation. So this describes not just the thermodynamic properties of the gas of molecules in classical mechanics, but it also describes their dynamic properties. So the fundamental object here is f of p, which is the density of electrons at a given density of molecules. You were thinking molecules, excuse me, with a given momentum p. So that molecule, each molecule can experience some force F. And the left-hand side is just a complicated way of writing down Newton's equations due to this force. So that's the left-hand side. Boltzmann's innovation was the right-hand side. And this is what's called the collision term. So every now and then the molecules in the room collide with each other. So here's two molecules colliding. There is some probability they will collide, and that's represented by this t squared. And then each collision has to conserve the total energy and also conserve the total momentum. And then you have to ask, how does the probability of collision depend upon the distribution of the molecules? So Boltzmann's fundamental assumption was that this distribution was just given by the product of the single particle distribution. So that's really the fundamental idea of Boltzmann, where you think of each molecule as statistically independent of every other molecule. There's no correlations, except briefly when they collide with each other. But other than that, the molecules can be really thought of as free particles, and every now and then they collide. And this collision scrambles their momentum in some random way. And so hence you get, as Boltzmann showed, an increase in entropy from this equation. It moves towards a more probable state. All right, so that's a quick introduction to basic principles of statistical mechanics, classical statistical mechanics. So the remarkable fact is that even this proposal by Boltzmann survived the introduction of quantum mechanics. So right now I'm applying it to the dilute gas of molecules in air. But now let's apply it to electrons in a metal. So then you get what you could call the Boltzmann-Landau equation. And if you look at these two slides, there's almost the same equation, except for one difference, and which are these 1 minus f factors here. So what are these factors telling us? Well, these factors are telling us that if when these two, in this case, electrons collide with each other, they're going to go into some other states of momentum P2 and P3. Those states have to be empty. And that's the exclusion principle that I'm sure you've heard about in chemistry, that you can't put two electrons in the same orbital with the same spin. And so here, this 1 minus f tells us that this better be empty, and 1 minus f P3 tells us that this better be empty. That's really all the difference you need to account for. And now, because of these factors, you have some very remarkable fact. So it turned out that collisions were very rare in a classical gas when the gas was dilute, because atoms had to find each other. Amazingly, in a quantum gas, collisions are very rare when the gas is dense. Because what happens in a dense gas is that the final states are either empty when you are at some very high energy, in which case these Fs, if it's high energy, these Fs are very small, or they're filled when you're at some low energy, then the 1 minus F is equal to 0, because every state is occupied and F is just equal to 1. So in fact, collisions hardly ever happen. They only happen at what's called the Fermi energy. The Fermi energy is the boundary between the occupied and the unoccupied states as you increase the energy. And so now the Fermi energy in any metal of the electrons that are moving around is, hundreds of 100,000 Kelvin or so. So at room temperature, you're much below the Fermi energy. And this term on the right-hand side is effectively almost always 0. So collisions are extremely rare. And so again, you can think of the collisions as statistically independent and really treat, for the most part, the electrons in a metal, even though the gas is very dense, as essentially free electrons. So you're neglecting, in this case, quantum interference or entanglement between successive collisions. Okay, so this is so now you can take this equation and now you can compare it with experiments. And this has been the foundation of solid state physics. Many books written on it, and I would say from the 1930s to, let's say, the 1980s, this theory was applied and was extremely successful, seemed to describe everything in sight. One of its predictions would be that in a metal like copper, that this time between successive collisions of electrons diverges as 1 over temperature squared as temperature goes to 0. This comes from solving the Boltzmann equation. And it's also proportional to the interaction strength, inverse interaction strength squared. So one consequence of this very long scattering time is that the resistance only increases as t squared. So this brings me back to the fundamental contradiction here. This is not t squared at all. So what's going on? Well, obviously, the assumptions behind Boltzmann equation, this assumption here, quantum interference between successive collision, is breaking down. Okay, it's one thing to say that, but it's another thing to then come up with a theory. But continuing with the Boltzmann discussion, one can ask, so you can ask, okay, let's start taking a system where the collision time becomes shorter and shorter. When would the Boltzmann equation start to fail? So if you look at that a bit more carefully, you find that there's a very fundamental limiting time. The tau has to be longer than what people are now calling the Planckian time, which is Planck's constant divided by Boltzmann's constant and temperature. So this is something, in principle, you could measure in a given material and conclude that as long as the tau is bigger than h bar over kt, you should find the resistance, Boltzmann applies, and the resistance should go as temperature squared. Now, this whole thing is self-consistent because if temperature goes to 0, tau becomes always much bigger than 1 over temperature. This is 1 over temperature squared. So everything seems to hang together, but somehow something is going wrong. And for some reason, I can't apply this result. So basically, it means that individual electrons are really cannot be described by their own distribution function. You really have to think about the whole system at one go. Okay, so here's another piece of data on the strange metals. Here they measure the frequency dependence of the conductivity. And Boltzmann equation would predict that sigma of omega is given by this formula, where this quantity tau of omega is actually frequency independent and proportional to 1 over temperature squared. And also m star over m is frequency independent. But here's measurements of this quantity is anything but. It's strongly frequency dependent and temperature dependent. And in fact, the typical value of tau is exactly this Planckian bound. So the bound is definitely violated because tau is not much bigger than h bar over kt. But we need a theory to show this behavior. Why is it kind of saturating at the smallest possible value? Okay, so that's my introduction to high temperature superconductivity, as shown in this phase diagram, and the very bizarre properties of the strange metal, where the very foundations of solid state physics, which are built on the Boltzmann-Landau theory, are seeming to break down. And it's clear that they're breaking down because we are neglecting the interference between successive collisions of electrons, or another way to say it, we're neglecting the quantum entanglement of the electrons. All right, so now for mysterious reasons that hopefully I will clarify by the end of my talk, I have to end by what time? Actually, can you remind me? I'm probably going a bit too slow. Around 9 to 9:40, would that be okay? All right, I assume that's fine. Okay, what are black holes? Well, this is one of the great predictions of theoretical physics. Carl Schwarzschild in 1916, while working with Einstein's theory of general relativity, found that there were some solutions of very dense matter so that light itself could not escape. And what he showed was that if you took a matter of mass m and squeezed it down below the horizon radius, here g is Newton's constant and c is the velocity of light, then light itself would be trapped inside the horizon forever. So, okay, that seems, quite a remarkable prediction. But if you put in, for example, the Earth's mass here, the Schwarzschild radius, as this is called, is only 9 millimeters. So you would have to compress the Earth to the size of a pea to make it into a black hole. So that's not happening anytime soon. But remarkably, there are objects out there, we know now today, many, many black holes, including a very big black hole at the center of our universe, center of our galaxy, sorry, which in fact has matter this dense. In fact, the matter is even denser than that. If you just imagine somehow a black hole formed, and this was became clear after the work of Chandrasekhar and Oppenheimer much later, that the matter inside the horizon would continue to collapse because of the gravitational attraction of matter to itself. In fact, would collapse to matter of point of infinite density. So that seems really quite ridiculous. How could this possibly? How could we believe certainly Einstein's equation with such dense matter, and open the question of what is really inside a black hole? So we still don't understand that, but we are made a lot of progress in understanding that, and I'm going to try to just give you an introduction to that topic too. All right, so the key thing, however, now it turns out to understand what's going on inside a black hole also turns out to be quantum entanglement. In this context, let's take EPR's thought experiment of taking two electrons, let's say, and separating them far away while they're entangled. And we separate them by throwing one of them inside a black hole. Now, quantum mechanics say that these two are still entangled. Okay. So this electron is still entangled with the other electron. And this has some remarkable consequences, which were deduced by Bekenstein and Hawking, although not exactly in this language. So what Bekenstein and Hawking argued that once you apply quantum mechanics and the ideas of entanglement to black holes, the black hole from the outside would appear that it has a temperature and an entropy. And very roughly speaking, what is the argument? The argument is that if I'm an observer outside with this particular electron in my hand, then this is truly a random state of the electron, because I can never find out. Like, nobody inside the black hole can ever send a message, because light can't escape, of what the state of the other electron is. So all the matter beyond the horizon is just lost forever. So this thing is really not entangled with anything in my observational universe. So it's essentially a random electron. And then Boltzmann taught us, once you have randomness, you have entropy and temperature. Okay, so that's probably a pretty naive and very simplistic argument, but it gives you the general idea of quantum entanglement leads to some very remarkable consequences. So using this type of argument, actually Hawking was able to do much more. He actually gave a number for the entropy of a black hole. And this is Hawking's famous formula, that the entropy is Boltzmann constant here, velocity of light, Planck's constant, Newton's constant. So really, first time that all these famous constants of nature came together. And A is the only thing that depends on the black hole. It's the area of the horizon, the surface area. And one way you can understand why the entropy is proportional to area is, as I said, the entropy is due to entanglement. And the entanglement is really happening only on the surface of the black hole. You have two qubits here that are entangled across the surface. And so it seems natural that it's proportional to the area. But from another point of view, this is totally remarkable because, as I mentioned earlier, any other system, like the gas in this room or anything else, the entropy is extensive. It's not proportional to the surface area; it's proportional to the volume. So something very special about a black hole. It's really the only object in nature whose entropy is proportional to the area, not the volume. Okay. Well, all right. So that's quite a remarkable result, and not everybody believed it to begin with, although today there's absolutely no doubt it's correct. And one of the questions it raised, which you can now see in the view as the battle stone between two famous gravestones. This is a Boltzmann gravestone I showed you earlier, written in the quantum language. And here's Hawking's gravestone in Westminster Abbey, which has the formula for the Hawking temperature, which I actually haven't written down yet. I will in a minute. And here's, I took the liberty of adding the Hawking's formula for the entropy of the black hole. So the big question this raises, of course, are these two gravestones compatible with each other? In other words, I have an entropy here, and I have a relationship between D and S here. So that tells me that naturally is a question, what is D for a black hole? What is the density of quantum states, D of E, for a black hole? Where are the degrees of freedom, which are presumably inside the black hole? Can you describe their dynamics such that they have the right D of E to give you this entropy? So that's the most fundamental question. And a lot of progress has been made in the question in recent years, and I'll tell you a bit about that. Okay, so let me just write down the two fundamental formulae obtained by Hawking for entropy and temperature. And these also imply one more very remarkable thing, which is the key to my entire talk. And that is, if you can now ask what is the relaxational time of a black hole? That is, suppose I have a black hole. It's a perfect sphere sitting there, and I throw a little star into it. Well, the black hole will distort and then eventually come to rest. And I can ask, how long does it take to come to rest at a slightly different temperature? Because now the area will grow, the mass will grow, and it'll have different temperatures. So how long does it take to come to thermal equilibrium? So that's what you would call the ring down time, which had been actually computed by Vishveshvara in 1970. But after Hawking's results, you can write it down in terms of the Hawking temperature. And amazingly, it's just this very simple formula. It's Planck's constant divided by Hawking temperature. So there's quite a remarkable connection between tau for black holes, the time it takes for them to equilibrate, and tau for a strange metal. They're all of the same order, the Planckian time. Okay, so that's really the connection why I'm talking about these two very different topics. And that was really the connection in my mind when I started thinking about black holes for the first time, and strange metals much earlier. And it turns out there's a common model. There's a much deeper connection now we now understand. And that's what I want to tell you about, why these two systems, the nature of quantum entanglement, really has some relationships to each other. Okay, one more thing about black holes I will need, which is that the most progress has been made in understanding black holes, which are neutral black holes, unlike which is the nature of all black holes and almost all black holes in our universe. But black holes with a net electric charge, Q. Now, if you solve Einstein's equation for such a black hole, you find that the horizon remains finite as temperature goes to 0. So there's some area at 0 temperature, A naught. So that's just a fact that I will need in the subsequent discussion. All right. Okay, so I have now introduced, two of the major puzzles in modern physics, both of which are moving towards some resolution. And the key is really to understand how quantum entanglement works when you have infinite numbers of particles. We don't have a full answer to that problem today. I mean, the varieties of entanglement are extremely rich, and a lot of people are thinking about different ways you can entangle particles. But I'll tell you here about a certain type of entanglement, which is turning out to be quite important in solving at least these two problems, superconductivity and black holes. So this is the entanglement that's described by what's called the SYK model of many particle entanglement. So let me first just, okay. So this is meant to be a little bit of a joke. So remember I showed you this Kekulé's theory of the benzene molecule. What he didn't mention was what Kekulé said about his theory, that he discovered the ring shape of the benzene molecule by having a daydream of a snake seizing its own tail. All right, that's what this picture shows. So I decided I have to have a dream. And so my spooky dream, I could say, was based upon snakes and ladders, which I'm sure, again, you've probably seen in your childhood. Although when I show this slide in the West, nobody knows what I'm talking about. So sometimes I show this slide, which is what the English call snakes and ladders, chutes and ladders. Okay, anyway. So what is the principle of this? Is that, you're connecting randomly different points on the square. And that's really all there is to quantum entanglement of electrons in the SYK model. So you pick a set of points, which I actually, instead of putting them on a square, I put them randomly. You have 19 points. And I put electrons in some fraction of them. I'm ignoring the spin of the electrons. Now I'm going to entangle the position of the electrons. So now these electrons are allowed to move, but in the model that we proposed in '93, they're only allowed to move in pairs. So for example, electrons 11 on sites 11 and 12 can move to sites 5 and 14. They have to move to empty sites, remember, because of the exclusion principle. And in quantum mechanics, every such process of electrons moving comes with a complex number, which I call U, 11, 12, 5, 14. So there's a certain complex number, and these electrons can entangle with each other and move to other sites. So there's some amplitude, U, 11, 12, 5, 14, for that to happen. And in fact, there's an amplitude for every possible allowed process. It's a different complex number. So if I want to solve the theory of these electrons sitting on these sites, I have to give you a list of these numbers. So you study the physical environment, you come up with a list of numbers, and then you take the list of numbers and you solve Schrödinger's equations, which will tell you what happens when all of these processes happen in parallel. That's quantum mechanics. Every one of these is happening together. And the only trouble is, once you get to beyond about 30 or 40 sites, those equations are too complicated to solve. You just even the biggest computer in the world today doesn't have enough memory to be able to integrate these equations and tell you what happens. All right, so what we discovered was that you can solve these equations in the limit of the number of sites going to infinity under certain conditions. And what was the condition? The condition was extremely simple, was that these numbers, this list of numbers, should be statistically independent. This kind of recalls Boltzmann's statistical independence of collisions. But here it's a fixed random number for each possible collision, but I'm not placing any restrictions on the distribution of the electrons. It's just I'm accounting for all the interference, but I just have to assume that these fixed amplitudes are independent statistical numbers. And amazing, that turns out to be a very powerful tool to allow you to predict what happens to these electrons. All right, so I won't go into the details of how that works, but anyway, you can solve it. And what you find then, is like the exact opposite of Boltzmann physics, where in Boltzmann physics, each particle was kind of independent, and rarely do the particles feel each other. But now you find the particles don't even exist. They're basically completely absorbed into an entangled quantum soup. And if you want to transport current, it would have to be some collective motion of all the electrons. All right, so those are just words, but we have theories of these things, but which you can watch some of my more technical lectures on YouTube if you're interested. But let me mention two properties that come out from the solution of the SYK model. One is that you in fact find, with a suitable definition of tau of omega, exactly this Planckian behavior. So this is something we discovered quite a while back, and we were quite excited because this was before anybody started really thinking about black holes in this context. We were very happy because this is exactly the type of thing that was being observed in experiments. On the other hand, there was another property that this model had, which was a surprise to us. This is in this paper with GPS. It seemed to have, it had in fact this property that the entropy as the temperature went to zero was non-zero. So if you take this order of limits where n is a number of sites goes to infinity, you divide by 1 over n to make it a number of order 1. So it's an extensive entropy here. And then you send temperature to 0, you get a non-zero value. Now, previously people had thought to get a non-zero value this way, you had to have the lowest energy state have a huge degeneracy. You need to an exponentially large number of states to have the same energy. And you could write down some very peculiar models. There's something called Pauling's ice model, which has that property. But that's not what happens here. Those models are really peculiar and they're highly fine-tuned. Here, this is not fine-tuned at all. I'm just taking some random numbers. And it has this property. And it turns out it has a property without the degeneracy. And it happens because the density of, say, d of E is exponentially large. It's some smooth function times e to the n s0. And here's actually a numerical data for a small system of the density of energy levels. So there's an envelope which is of order e to the n s naught. And that's sufficient to give you a non-zero ground state entropy. Zero temperature entropy. And what I realized in 2010 was this property is in fact just the ticket for black holes, because I remember this property I mentioned here. The black holes, it had been known earlier, but people, I wasn't known to me at that time, but people knew that charged black holes had this property that the entropy was non-zero, even at the limit of zero temperature. All right. So when I learned about this in 2010, I immediately made the connection that, okay, there's a connection here, possible connection, not only from the Planckian time, but also in the entropy. And that's the connection I proposed in 2010, and now it's become a much more complete theory with all kinds of details worked out. So I will very quickly, so here I'm getting a bit more technical, but I'll just quickly flash through this. I'm getting towards the end of my talk. So how would you really compute? Let me just say what these equations mean. How would you really compute the density of states or the entropy of a black hole? Well, the principles of statistical mechanics and quantum mechanics are quite precise. They tell you that you compute what's called the partition function, where you do an integral over all the classical fields. In this case, the metric and the gauge field of Einstein and Maxwell theory of electromagnetism and gravity. And this is in 3 space and 1 time dimensions. Okay, so here's a picture of a black hole. with a charge q. I'm going to call the two transverse directions x and the longitudinal direction, the radial direction, zeta. And so those are the three directions, and one is time. Well, it turns out that for a charged black hole, there's a simplification. You can, at low energies, you can actually ignore the x direction. You just ignore the x direction and only worry about the zeta direction. So that's great, because you end up with a theory in one space and one time dimension. And you have to pull out the Bekenstein-Hawking entropy factor that just comes out of this calculation. This is how Gibbons and Hawking obtained it some time back. All right. So now this factor here is exactly the analog of the GPS entropy and S naught. And we're left with this more complicated quantum theory in one space and one time dimension. Now here comes the remarkable fact, which was shown by Kitaev and Maldacena in Stanford, that even this part connects up to the SYK model. If you take this theory and look at its low energy limit, it turns out to be exactly the same theory you would get from the SYK model, which is in zero space and one time dimension. So that's a very explicit connection between the zero-dimensional SYK model and the three-dimensional charged black hole that you might find out there in the universe. And amazingly, you get the same low-energy theory whether you start from Einstein gravity in three space and one time dimension, or you start from this toy model of electrons with random interactions. You get the same theory, amazingly. And there's some deep reasons for this connection, but I don't have the time to go into those. Anyway, so you can now evaluate this quantity and, in fact, then evaluate the D of E for a black hole and go beyond the Bekenstein-Hawking answer. So this is the current status of this result through the contribution of many people. This is the D of E of a black hole. There's something inside a black hole which has this density of states, we now know. This is the Bekenstein and Hawking only gave this exponential factor, which is energy independent. From the SYK model, we now know the energy dependence is this smooth function of energy that vanishes as energy goes to the lowest possible energy, the sinh squared of energy. And these are, everything involves only the fundamental constants of nature and the area of the black hole at zero temperature. And there's an overall prefactor that was just obtained recently. This is beyond the SYK physics. Okay, so that's the answer. Now, some of you may have heard that something called string theory described black holes. Well, string theory was applied to supersymmetric black holes. These are very special type of black holes that appear in more general theories of gravity, not just Einstein gravity. And they gave a very different answer. They gave a D of E, which was in fact more like the degenerate answer that of Pauling's ice model. So here it's supersymmetry that fine-tunes this answer, gives you degenerate ground state. But that's not what we now understand happens in actual charged black holes, which are not supersymmetric at low energy. Okay, so that's, what is inside a black hole? Well, this picture is meant to, I wouldn't say there actually is an SYK inside a black hole. It's probably string theory in there. But from the outside, it appears as if you can compute almost everything, assuming there's something like an SYK model inside. Okay. So, all right. So I have a few more minutes, I guess. So now very quickly, let me return to my original love, which was superconductors, which is the reason I introduced the SYK model to try to understand the Planckian time dynamics. But this, it's not reasonable to take the zero-dimensional SYK model and apply it to a superconductor. Quite remarkably, the zero-dimensional SYK model became just what was needed to describe charged black holes in three space and one time dimension. But that's not reasonable for superconductors because, for one, superconductors don't have a zero temperature entropy under any situation. So what's going on? But they do have the Planckian behavior. So how are we going to make this work? Well, we really have to go back and think about the physics a bit more. So I mentioned the strange metal and the ordinary metal. So I need to tell you a bit more about what's going on here. So the ordinary metal has some other properties, which I have not mentioned so far. It has what's called a Fermi surface. So I mentioned the Fermi energy, which is the boundary between occupied states and unoccupied states of electrons. Now you can put the electron states in momentum. So this is the momentum space. And in momentum space, we know from experiment, this is actually experimental data, that all of the states of the electrons inside these two lines, these are the Fermi surface lines, are occupied. So everything in here is occupied and everything out there is empty. So that's the Fermi surface as measured of yttrium, barium, copper oxide, or some related material. And amazingly, it's exactly what you would predict if you treated the electrons as essentially free. If you took a model of free electrons, you would in fact get exactly this Fermi surface. So that's exciting. Everything is working. On the other hand, if you went down here in the red region, which is we have what's called a pseudo-gap metal, experiment shows something very bizarre. The Fermi surface seems to have broken up into little pieces. And so there's been a change in the nature of the Fermi surface. So what we have proposed that it's this change in the Fermi surface that's really the most fundamental thing that's happening here. And in fact, the basic phenomenon that's also responsible, this we haven't proven, but that's the hypothesis for the high temperature superconductivity. So to establish this, what we first need to do is just get rid of the superconductor and just think about the change or the quantum phase transition between these two Fermi surfaces. So let's get rid of it, at least as theorists, and now try to understand this hypothetical phase diagram. So you have to study quantum phase transitions of Fermi surface change between, okay. So that's a topic that I've worked a lot on, and many other people. And there are many theories of this Fermi surface change, and they typically involve coupling the electrons to some boson, with some emergent particle. And as you tune the mass of the boson, you can go from a state where the boson is condensed, that's Bose-Einstein condensation, and the Bose-Einstein condensation of the boson leads to this deformed Fermi surface, to one where it's not condensed. And so it becomes a theory of understanding the Bose condensation in the presence of a Fermi surface. So that's really what it's all about. And there's a coupling between the boson and fermion, which is called a Yukawa coupling. Anyway, so this has been studied, and to summarize several decades of work, people do indeed find at the critical point that the electrons are strongly entangled with each other. So does this give a strange metal? Unfortunately, the answer is no. If you take this model, it gives you entangled electrons, but it doesn't give you the right transport properties, electrical properties. So this is where things stood, and recently we think we have had a breakthrough due to some insights, especially by Avishkar Patel, one of my former students, that we realized that what we have to worry about is the impurities in the material. So remember I mentioned these oxygen that goes away from the layers. That goes in random positions. So you have to study a system with random positions of the oxygen. And it turns out the way to do it is in fact using insights from the SYK model, where you take this Yukawa coupling and make it a random functional position, and that works. All right, so from that we can get the linear to resistivity, we can get the optical, this is the experimental data, this is our theory, this is the tau, and that also comes out in a theory. So I know I'm rushing through, but in the end, you just have to take my word for it. It seems to get all the observed properties, this Yukawa SYK model, where you get the tau of omega, and the entropy does vanish in this model as T log T, unlike the zero-dimensional SYK model. Okay, so let me just conclude. Basically, I've talked about multi-particle entanglement in the SYK model, resulting in loss of identity of the particles, where Boltzmann's equation breaks down completely. And some extension of this model, called the 2D YSYK model, actually is matching well with the experimental data in the cuprates. The next step is to really show that it explains high temperature superconductivity, but you're not there. These are things we're working on. And quite remarkably, in fact, it's had a much more precise and led to much stronger advances in the theory of black holes, where there's a dual set of variables with the SYK model, in fact, has led to a computation of the low energy density of charged black holes, but also, which I have not described, lots of advances in understanding how quantum information leaks out of a black hole, and resolving in some way Hawking's information paradox, which is also something I've not talked about. All right, thank you very much.
Thank you to our esteemed speaker, Professor Sachdev, for shedding light on this captivating topic. And thank you all for being a part of this entangled journey. We hope you all enjoyed exploring the mysterious world of particles, their interconnectedness, and the mind-bending implications of entanglement. We are now open to taking questions from the audience to make this process smooth. We actually have taken notes of the questions that were in the charts. So we will be asking one after another of them. Is it okay, sir?
Okay. Sure. Oh yeah, I see. Oh yeah, the chat. I wasn't looking at the chat. Oh,
Yes,
okay.
sir.
Yeah, go ahead. Yeah.
Yes, so the first question was, so the two states got delocalized in the previous slide by Mrityunjay Sahu. Actually, it was of the slide that had quantum entanglement of green slide. The third or fourth slide, sir.
Okay. Let me see.
Otherwise,
You can.
Mrityunjay, you can unmute yourself and ask the question.
Okay. Right. Yeah. So let's see. You can see my screen, right?
Yes, sir.
Yeah. Okay. Here. What is the question?
So the question was, the two states got delocalized or not?
There's only one state. I mean, I think that's the way to say it. There's only one
So the
state, and
green
that's the
slide, I
entangled
am
state.
talking about the green slide that has a text in green. Yeah, that one, sir.
Text in green. This one?
Yes, sir.
No,
Yes, this one.
this one. Yeah.
So next one. So the next one.
This one.
Yeah, this one.
So which two states are you referring to?
Mrityunjay, can you kindly turn your mic on? I think, sir, he is not right now present.
Okay, well, I think he's probably referring to this, and I guess I would say that there's only one state, even though there are two electrons, they share the same state. That's the essence of entanglement. All right, so I can see the question there. So the next question is, why is the graph of a superconductor irregular in shape? I presume you mean this little bit, this dimple over here. That's an excellent question. So here, this little dip appears at when this number is 0.12518. So when the density of holes is exactly 1/8, it turns out there's some special states that can form with the charge density wave. So that's kind of commensurate with the lattice. So it locks in. And yeah, so that's another topic of research we didn't talk about, but yeah, okay, that's what it's due to. Metal does have linear dependence on resistivity temperature. Why is it called strange? Yeah, we definitely need a better word, but that's the word that stuck. I don't know. I think it was Patrick Lee who came up with it at some point. It's strange because, well, it's different from ordinary metal like copper, where it wouldn't be T, it would be T squared. In the second side representing benzene bond and electron pair state, why was the singlet minus instead of plus sign? Oh, right. Great question. Again, something I didn't explain. Where is benzene? Let's back up here. Yeah. Well, yeah. So this has to do, with the nature of the electron interactions because they repel each other, and the repulsion leads to the fact that the spin of the electrons like to be anti-parallel, and when they're anti-parallel, it's only the state with the negative sign uh, that has a lower energy, that has total spin 0. In other situations, they could be ferromagnetic. So the plus sign actually corresponds to a ferromagnetic state, not up down. So up down plus down up turns out to be the state where they're both just parallel in the x direction. That's just a property of a qubit. Okay. Quantum mechanics treats electrons as particles with no size. Then how can their collision be defined? Oh, great question. So let's see. So that's Boltzmann's equation here, for example. Yeah, well, the electron is a particle with no size, but it has a wave. That's the uncertainty principle. So even, uh, it has a finite momentum. So if it's a finite momentum, it also has some finite size. And so it has what's called a wave function that describes the uncertainty in the position of the electron. And so there can be a collision, and you can compute what's called a collisional cross-section. That's this T that goes in here. So that's the easy part. You can compute that and then put it into Boltzmann and Landau told us which equation to stick that into. And then you have to solve this equation. That's the hard part. But we can do it quite systematically. Why the density of black hole needs to be infinitely dense rather than the amount required for the Schwarzschild solution. Well, so what Schwarzschild was solving was a static problem where he assumed there was some mass, m, and he was solving Einstein's equation in free space. So there was some mass m inside this radius r, and he was just solving in free space Einstein's equations. There was just a boundary condition that inside the horizon there was a mass m. Okay, so he wasn't making any further assumptions about that mass other than the fact it was spherically symmetric. So with that boundary condition that somewhere inside the horizon there's a mass m, you could solve it and then find the horizon. So there's no actual mass over here at the position of the horizon. It's still free space, but the space-time geometry is distorted by the presence of the mass inside. He didn't know what happened to the mass inside. This was 1916. In fact, the final form of Einstein's equations did not appear till 1918. But there were some early versions that he was working with. Okay, but the new version didn't change this result. So then, the question is, how do black holes form? So that's what I addressed over here very quickly. Well, so black holes form, we know today black holes can be the final state of stars. Now stars, what's happening in an actual star is that their nuclei, there's a lot of nuclear energy, fusion energy being generated by the fusion of nuclei, and that's what really keeping it going. So that keeps it of a certain size that wants to expand the black hole, whereas gravity is always attractive. It just wants to collapse. Gravity, everything attracts in gravity. Now, eventually the nuclear fuel burns out or something, and then the star is going to collapse. So what people had thought it would collapse into, what are called white dwarfs or neutron stars. And then Chandrasekhar showed that there was a certain mass beyond which the white dwarfs would not be stable. So that led to a huge problem. What happened if you had a star just beyond the Chandrasekhar limit and it collapsed under the right conditions? All right, so this is I'm entering now an area which I'm no longer an expert, or I know very little about, let me say. Uh, anyway, this was what was addressed by Oppenheimer and Volkoff in Oppenheimer's probably most impactful paper. And they deduced that in fact it would form a black hole. People were skeptical, but that's what happened. So what's happening here is the black hole has formed. There's matter inside. The matter no longer has nuclear fusion of any appreciable amount. And so only gravity is present. So it'll just continue to collapse to some forever. If you just had gravity, there's no limit. It's just going to collapse forever. Of course, it's not just gravity. There is eventually the nuclear force, the electrical force, and quantum mechanics will come into play. And that's what ultimately determines what's inside the black hole. But we don't have a complete theory of that by any means at this point. The amazing thing is we can make a lot of progress on the quantum properties outside the black hole, as I've argued, without really knowing in detail what's inside, because many of those properties only depend on general properties of the entanglement. The idea of black hole entropy being proportional surface area is still very counterintuitive to me. Is it not possible to have two entangled states across the event horizon of a black hole and not only along its surface? How is the problem present? Yeah, so the answer is yes, it's possible to have two entangled states of a black hole, not only along its surface. But really what we're talking about now, something that's happening on the black hole is just sitting there. Nobody's throwing anything. And these are quantum fluctuations. So, quantum mechanics by its very nature can allow many things to happen for a very short time. And so you should think of these as virtual quantum fluctuations. And if you have a virtual quantum fluctuation like this on the surface, where one side gets pulled inside because it's inside the horizon, the other side, manages to escape. Well, that's only going to happen right on the surface, and it's only those virtual fluctuations which separate the pairs that are going to lead to entropy. Okay. What does mean to black hole have a charge? Does it respond to electromagnetic field? Yeah, that means there are more electrons than protons, for example. So it has to have our other way around. So that's probably not. Electrical forces are much stronger than gravitational forces, at least at reasonable length scales. And so when stars form, they're pretty much neutral, because if they had an excess of protons, they would just attract the electrons from far away and become neutral. So to form a charged black hole is a tricky thing. Probably there's nothing out there, unfortunately. But nevertheless, you can theoretically imagine a universe in which there are more protons than electrons, and then they will form a charged black holes. Okay, great question. These are all just amazing questions. What is the Fermi surface of a superconductor? Again, a very perceptive question. There is no Fermi surface in a superconductor. So the Fermi surface is a property of the metal. So what happens in a superconductor, which I didn't talk about at all, is that the electrons start to pair with each other and form a boson called a Cooper pair. And when that boson condenses, this is a different boson than the phi boson I showed earlier, you get superconductivity. And one of the things that happens when the electrons become bosons by forming pairs, then the Fermi surface disappears. What role does entanglement play in measurement-induced decoherence, and how does this interplay affect the transition from quantum superposition to classical reality? Okay, well, that's a very deep question, which I don't think I can answer. Well, what is measurement-induced decoherence? Well, so that is when you look at something and that decoheres the electron. Okay, another way to, what role does entanglement play? But another way to talk about measurement is also entanglement. but it's an entanglement between what's being observed and the observer. So what's happened when you measure a bit and you collapse it, it's really entangled with the observer. Now you're putting in some information. You're saying, well, the observer saw this. Okay, well, the observer saw this, then that forces the observed bit to also be in a certain state because the two are entangled with each other. Yeah, so that's really, measurement is also entanglement. It's just an entanglement between the observer and the observed. Now you can ask, what if the observer why isn't the observer himself feel the entanglement? Well, that's a philosophical question. We do a measurement, we design an apparatus to give a very definite answer. It gives an answer. If it didn't give a definite answer, we would say it's not a good measurement. So you design it to give an answer, and then we are in that state where you got that answer in that part of the state. What about the rest of the state where there's no answer? Well, that's not a logically consistent thing because we're not talking about any observation at that point. That's getting into philosophy that I don't want to get into. If you just restrict yourself to what is observed and what is, quantities that you can define that are observed, then there's no contradiction. Is the wave function really real? Is the part of the wave function that you didn't observe, is that real? These are philosophical questions. Okay. Finally, what from the SYK model can the density of can we just explain density of energy states of only charged black holes? What about uncharged one? Well, that is one of the big open problems in physics. Yeah, the answer is no, you cannot explain it for uncharged black holes for this very simple reason. If Q goes to zero, A0 goes to zero, and you don't have a black hole. So none of this works for uncharged black holes. So uncharged black holes are a lot more difficult. In fact, today we don't know what the answer is. And many people are working very hard on that question. So that's really one of the very difficult open questions in quantum gravity. Amazingly, if you put a little charge, everything seems to be now much better understood. Even string theory has nothing to say because the string theory black holes are also all charged. String theory, nobody knows how to solve string theory for uncharged black holes. Okay, any further questions? Those are all wonderful questions.
That's all, sir. Thank you very much, really. And we are really obliged that you took time. And thank you once again, Professor Sachdev, for taking time out from your busy schedule to embrace us with your wonder of quantum entanglement, the invisible threads
Okay.
that bind our universe together. We hope to hear you from again soon. We thank our faculty advisor, Dr. Rahul Sharma, for joining us too.
Okay, thank you. And please send me a link to the recording when it's
Sure,
uploaded.
sir. Thank you all the
Okay.
audience for joining us today for this fascinating discussion on this beautiful topic. We look forward to meeting you all in the upcoming talk. We all wish you all a very good day. Thank you very much.
Thank you very much.
Thank you very much.